طلبة الأعزاء، السلام عليكم ورحمة الله وبركاته. نكمل المحاضرة رقم 4 ووصلنا للمثال رقم 4. وبهذا المثال راح تلاحظون أنه يطلب التصميم للكونكريت ديزاين ميكس using both the American and British method. فهنا هذا راح يصير الحل بالطريقتين في آن واحد. فهاي هم نموذج من نماذج بعض الأمثلة. ممكن نفس المهندس يحب يصمم بالطريقتين ويشوف الفروقات لأجل يصير عنده احتمالين أثناء ما يسوي ترايل ميكسز بعد ما يكمل التصميم اليدوي. فلو تلاحظون المعطيات مثل باقي المعطيات الموجودة بباقي الأسئلة إنه using both the American and British method design a concrete mix to bear an average compressive strength of 30 megapascal at 28 days to cast a room slab with the following dimension, the same dimension as we have in the previous examples. Also we have one of the quizzes that has the same dimensions, and 200 millimeter space distance of reinforcement, and consider the following properties. Cement use is type 1 Portland cement with a specific gravity of 3.15, requires slump 30 to 60, coarse aggregate details. If you can see in the details here, it's been designed in a way that it can provide a clear information for both methods, the British and American. So in terms of the coarse aggregate crash rocks, maximum size of aggregate is provided, dry rodded unit weight that we need to use in the American method, so it's provided under the coarse aggregate. We have the bulk specific gravity and absorption capacity. For the fine, it's a crash rock as well. It's a fine modulus 2.6, bulk specific gravity is 2.6, and the fine aggregate falls in zone 3. Also assume zone A for figure 1, that's for British method, and assume K is 1.64. And note, please, do not adjust the amount of water in the mix design. So these are the main information that we are going to use to do the the mix design for using both the American and British method. So we first start with the American method, and we follow the same steps we learned in the previous examples and lectures. So first we check the slump, and the sum is okay. If we go and check to table 3.7, because here we have the slab, and in terms of the slab, if we go and check for the slabs, so so we have structure walls, footings, okay, pavement and slab is 20, so it falls between 20 to 80, and the one we have in the example is 30 to 60, so that falls within the recommended range of slump, and that should be okay. We go then to check the maximum aggregate size, which is the same step we used in the previous example. And if you can have the third of the depth of the slab and the 3/4 of the space distance between the reinforcement, that should be okay. So the 40 is okay. Then we go to the mixing water, and we go then and because there is no mention to a freezing and thawing in the example, so there is no exposure of any kind. In that case, if we go to that table, so we have the aggregate size as 40. It is non-air entrained because there is no exposure of any kind. And then we can have the slump. So the slump in this case, the one we have in the example is 30 to 60, and the one we have in the tables have 30 to 50, 80 to 100. So the one we need is the 30 to 50 because it's the only one that matches the requirement. We cannot go and take the 80 to 100 because it exceeds the requirement. So 30 to 50 and corresponding to 40 mm for the aggregate size. It is non-air entrained, so so that's it. It's 160. Okay, so in that case, as we said, is non-air entrained, and for against corresponding to slump of 30 to 50, so it's 160. Also, we have an approximate entrapped air content, which is 1%. So we go and fill these information in the relevant steps. So we have 160 and 1% air content. And for step 4, we have the water and cement ratio. We go to table 3.1 and we check that table 3.1. So what we have is non-air entrainment, and we have 30 megapascal corresponding to 0.55. So 0.55 is corresponding to strength of 30 megapascal. And for step 5, here we have calculation of cement content by using the information we have in step 3 and 4, dividing the water content over the water cement ratio. So we have the 290.91. So it's all the same as we did. So you could just do that straightforward. And also we have the information concerning the course aggregate. So in that case, you have the, the fine modulus, which is 2.6. And if we go to that table, then we could get the, the volume, the dry volume as 0.73. If we quickly go and check, so quickly checking, so that's the 40 and that's the 2.6. So there we go. Okay, so then multiplying that by the dry rod density and then convert it to the SSD by adding the absorption capacity, so we get that amount. Then we go to step 7, estimation of fine aggregate, and in that case, as long as there hasn't been any mention in this example that you need to use a specific method, so it's up to you to use either the weight or volume method. And the easiest method is the volume method, and in that case we have all the information we need. We only need to divide everything against the the density of its corresponding materials. So in that case we have it in this formula and we are set. And if we subtract all these quantities, all these volume from 1 cubic meter, then we get the volume of fine aggregate as SSD, and then multiply that with the density, so we have it the fine aggregate's weight, SSD. So once we have it, we could then divide everything over the weight of the cement. Okay, and we all set. Then we get the proportions, and then we could fill that table and everything will be okay. So then we could go and use the same information and do the design mix, or the mix design, using the British method. And we follow the same steps you have used in your homeworks, and the one that we explained in the previous example. So we use the same formula. We first find the target strength, and by applying the formulas, here we have the K is provided, the S it says zone A, so we could just correspond the 30 megapascal against the the right curve, and then we get the 8. So we have 8 megapascal, the standard deviation 1.64, the K multiplied by the 30 plus multiplying the M, so that will be the 43. Then we go to that table. So we have ordinary Portland cement crushed rock corresponding to 28 days, so that's 49. So once we get that amount, then we could just draw it and intersect that line with the that vertical line corresponding to the water cement ratio at 0.5, and then we draw that parallel curve, which to be parallel to other curves, and then we use the target strength and cross it with the new curve we have drawn using that information provided with the 49, and then as a vertical drop to the x-axis, we get the water cement ratio, which is about to be 0.55. So once we have that, then we could have the step number 4 and get the free water content All the information we need to get this amount of water is provided. We have the slump 30 to 60. We have the aggregate size 40. We have the type of aggregate, which is crushed in that case. And so it's correspond to 190. So there is no need to use this formula as we explained in the previous example. We can use it only if we have one of the aggregate is uncrushed and the other one is crushed. So 190 it is. We go to step number 5 and finding the cement content. So by dividing the water over the cement, water cement ratio. Then we move to step number 6, and in that case we haven't got any information concerning the relative density of the combined aggregate. So in that case we use the one of these that correspond to the type of aggregate, whether it's crushed or uncrushed. In our case it's crushed, so we just match these information on this diagram, and then we get the relative density as 2420. Then we could move to step number 7, and we just a straightforward step. We just have the information and then we get the total aggregate content. Once we get that, we can then move to step number 8, and as you know, we need to choose the right table. The information provided is the size of the aggregate, the slump, and the zone. So once we get this information, then we could choose the right diagrams. Once we get it, then we could just have this information applied on this diagram, and then we get the the proportions, the start point and the end point. In our case, the start point approximately is 25 and the end point approximately 29. So the average of it is 27. Once we get that, then we could get the proportion of the fine aggregate, and afterward then we get the coarse aggregate by subtracting the fine aggregate from the total aggregate. So there you have it. Once we complete all these calculations, we could just fill that table, and also we could have this proportions made by dividing all these informations and these weights over the cement weight. So 190 divided by 345, and so on and so forth. Okay, so that's it. That's for the example. In case we get you need to design the make your design mix using both methods, and then you could compare which one is the most economic one, and then you could use it as a trial mix. And now we move to example number 5. So example number 5 is a follow-up to example number 4. فهنا أحيانا شنو يصير إنه ورا ما تخلص التصميم you could use the تستخدم نفس المعلومات اللي تحصلها البروبورشنز من التصاميم اللي حصلتها، وإنه بتقدر تطلع الكميات المطلوبة لصب فد هيكل إنشائي معين. مثلا in our case in example number 5, using the design or the mixed design obtained from the British method. So كل المعلومات اللي حصلناها من British method, we're going to use it in this example. So how much of each individual ingredient is the same example as you have in your homework and in lecture 2. So it should be used to cast a room slab with the following dimensions. Consider 5% extra amount. Consider the following properties. So all the information you need is provided, and in our case you could use the same unit weight you have obtained from the British method. So whatever information you have derived using the British method, you can use it in the example number 5. Okay, so if we look at the proportions for the British method and the American methods, and if you make a quick comparison, you will find that the American method and the British method, the British method is much more economic in terms of the weight of the the aggregate and the sand. So now we could just apply the same step we have used in lecture number 2. So the mixed design is the one we have here. Okay, that's it. And now we first, get the volume of the specimen, which in the example we have is a slab, and then we have the weight from the British metal, which is 2,420. So by getting the weight with the extra, so the total weight will be 10,164 kilogram. So now we calculate the weight of the cement, and once we get it, then everything will be easier to get. So we multiply, we get all this information in here, and then we get the WP, which is the weight of the Portland cement, and which is 1,452. Okay, so all set now. We have calculated the weight of the Portland cement, so everything should be easy. And now we get the sand by doing all these steps we did before, and then subtracting the stock from the SSD. We get that amount of mortar that should be subtracted from the the design water mix. Similarly, for the coarse aggregate, we follow the same calculations we have learned in lecture number 2 and in the homework as well, and subtracting the stock from the SSD, and we get minus 31. In that case, the gravel will absorb water, so we need to add this 31. So we do all this calculation concerning the water, and that's it. Okay, so it's easy peasy. You could just it's a straightforward example. You could just do it in less than 10 minutes. Okay, so that's it for the for lecture 4. وإن شاء الله احنا بالمحاضرة رقم 5 راح ندخل بأمور أخرى.